Yeah. I love it.
Okay, I will get started for the sake of time. People always pour in here because they can't find it. So, it's a great pleasure to introduce Dr. Sam Blau from LVNL. Sam started working for Josh Ryer and Alex Norquist at Haverford, and then did a PhD with Alana Spruger-Guzik at Harvard, working on, I think, exciton transport in photosynthetic complexes, and then moved to Berkeley to do a postdoc with Christine Pearson. He is an expert in a lot of things, but I think the general focus is on energy materials and computational machine learning approaches for designing things there. And we're very excited to have him here today. So please welcome Sam.
Thanks, Nick. Thanks for having me. Thanks, everyone, for being here. My first time at UC, really beautiful campus. So glad to be here and looking forward to telling you about a mouthful. Leveraging null representations in ML model differentiability for kind of two quite different areas of optimizing heterostructured nanoparticles and calculating reaction transition states. So if my clicker's alive. There we go. Good. I'd say that the not so secret sauce of what makes machine learning powerful and possible is a combination of two things. One is that the ability to represent the types of systems that we care about in a way that is appropriate and kind of information dense for machine learning. Here, I'm just not going to go through this, just showing that molecules can be represented as graphs, which makes them well suited for machine learning applications. But the combination of those, the other side of the coin is the importance of automatic differentiability, which is essential for training our neural networks, but also is kind of a key benefit of a trained model. It's not just like a faster surrogate model, but it's a faster differentiable surrogate model, which kind of gives you access to techniques that you wouldn't otherwise have. So kind of these are the importance of representations and differentiability, and the overarching themes of the talk. It's really two talks in a trench coat, but I'm first going to tell you about some work we did. We're building a data set of simulated nanoparticles. We came up with a new representation for how to do machine learning on them. And we used the models with our representation, trained on our data to perform gradient-based optimization, which we kind of take a key out of Alana Spruger-Guzik's book and call it inverse design. It's really gradient-based optimization, but if he said it and got away with it, I'll say it and get away with it too. And then the second part of the talk is kind of much more in the chemistry domain. This nanoparticle work is quite a bit different from anything else that I've done. I'm really a computational chemist. I think about atoms and molecules, and I care a lot about transition states and picking apart complex reactivity. And in that context, we are using a neural network representation of our reaction path to optimize transition states more efficiently, more robustly, and improve on previous top machine learning potentials. So, kind of in the hope and the assumption that machine learning potentials are on the way to replacing DFT. Now, what's the best way to find a transition state atop a machine learning potential, where we kind of go beyond previous methods? And both of these are kind of unified by the importance of representations and differentiability, and also the importance of data. But I'll mention that a little bit. So to start with, let's talk about nanoparticles, something that a few years ago I knew nothing about, and now I know a little bit about, enough to do some interesting work. So these are upconverting lanthanide-doped heterostructured nanoparticles, where you've got basically these lanthanide 4F manifolds. You can absorb photons, get up to a higher energy level, and then emit a higher energy photon. So in this way, you can take kind of a long wavelength light and upconvert it into higher energy short wavelength light. And these types of particles have a bunch of applications in super resolution imaging, lasers, optogenetics and therapeutics, subsurface imaging and sensing, 3D printing, all sorts of places where you want to be able to use one wavelength of light that passes through some medium and then locally deliver higher energy light at the site of your nanoparticle. And what's kind of really cool about these things is that the heterostructure controls their photophysics. So you have some undoped inert host, And then you have your whole range of lanthanides, which you can now swap out and dope your, different regions of your nanoparticle with different concentrations. And so here now we're kind of breaking it down into a core and two shells, where each region has different concentrations of these dopants. And thanks to the magic of robotics and many years of hardworking synthetic nanomaterial scientists, we can make these with high precision, kind of get exactly, we can control the specific dimensions, the thickness of each region, the precise concentration of the dopants in each region, and that allows us to kind of build these intentional heterostructures, which then control the photophysics. Because what's happening here is that you've got these different energy levels from these different lanthanide dopants, and then you can have energy transfer. You absorb light, the lanthanides absorb light, they pass energy between them. And so, in this example, if you have neodymium and erbium in the same region, then they kind of have this cross relaxation, they kind of quench each other. Versus if you absorb a neodymium, transfer to terbium, transfer in space over to eventually erbium, now you can get emission. So separating these dopants and kind of controlling how much of each one is in each region and the thicknesses of each region allows you to control the photophysics. So this is kind of representation. I'll be using not a machine learning representation, just a graphical representation to kind of depict a nanoparticle with different thicknesses of regions and different amounts of doping. So I'm not saying that like all the ytterbium is over here. I'm using this as a pie chart saying that the core is all homogeneously 40% ytterbium, 5% erbium, and then 55% host material. And then, of course, kind of the radii are depicting the thicknesses of the regions, right? So just pie charts, but within a region, you are homogeneous. And what's kind of blew me away when I first started this project was the fact that we can actually simulate the photophysics of these nanoparticles pretty well with kinetic Monte Carlo. I come from DFT and I hear tens of thousands of atoms and F block dopants and all these electronic levels. And I'm just like, oh my God, we have no hope. We have no hope. But some really smart and diligent people in kind of the 50s and 60s worked out all the kind of energy transfer rates between all these sites. And I mean, it's not perfect, but it's pretty good, which I still find shocking. So we generate an ensemble of randomly doped 3D structures because we don't know exactly where the individual atoms are. We know the concentrations overall in a specific region. So you can then kind of randomly swap out your host for your dopant to match your concentrations. You get an ensemble structure. You can run KMC and you can predict the emission spectra of these particles. Again, wow, amazing, great work. And we also implemented, Emory for many years been doing this in Igor Pro 7. I'd never heard of for this project. Doesn't run on Linux, God forbid. So we re-implemented it in C++ and made it a bit faster and made it so we could actually like run it on a supercomputer rather than just on your little Dell workstation. And so that's great. It's nice and efficient, but it's still computationally expensive and it's not parallelizable. You're talking about 10 to 250 hours on a single CPU core. And this can be much longer than that. I mean, I'll tell you later about some of these trajectories we have to run for 3 months. Okay. And we're working on a supercomputer where you have a 48-hour wall time limit. So you've got to be constantly checkpointing and restarting, and it's a big pain in the butt. But this is why no one's kind of made a data set of these types of things before. And really, you have this problem of combinatorial complexity. Just think about a core in 9 shells, 10 spatial dimensions, 3 dopants, so 3 kind of concentrations in each region. That's a 40-dimensional search space. And this isn't some nice, well-behaved, smooth thing. Photophysics is highly nonlinear. So it's a really complex nonlinear landscape you're trying to kind of search through. And Emory has these amazing robots. You can do all this synthesis in high throughput, but even still, to synthesize and characterize and do optimization in this kind of 40D plus search space is not really viable. So you can do high throughput KMC simulations, but even then, it's just way too slow for global optimization in 40D. And there's no gradient information, right? Let's remember coming back to these, we'll come back to these gradients later. You're going to get your emission, but not like the gradient of the emission with respect to a a layer thickness or a dopant concentration. So you're basically going to be stuck doing like Bayesian optimization rather than something more efficient. So really, that's why we say this problem demands inverse design. Again, borrowing from from an Elan science paper where they called gradient-based optimization atop an ML surrogate ML model inverse design, but really it's gradient-based optimization. So that means we need to build a data set and have a representation. These are kind of the key missing ingredients. There are no large-scale data sets of these types of simulations of heterostructured upconverting nanoparticles because they're really expensive and because the best implementation until this project was in EOR Pro 7. And we need to connect to the heterostructure to the properties in order to machine learn it. We also need better representations. This is not a molecule. This is not a unit cell where an atomistic representation is going to make sense. We need gradients of emission with respect to structural parameters like dopant concentrations and layer thicknesses, which no previous representation could do or even could learn very well at all. And really, we're kind of focused in this part of the talk on these heterostructured upconverting nanoparticles, but I would say that these are fairly general common challenges across different types of nanomaterials, the lack of data and the lack of representation and the need for kind of inverse design. So just to kind of give you a quick overview, we went all the way from building the first large-scale data set of these simulations to playing around with and thinking through the different types of representations, developing a heterogeneous physics-infused graph representation for these heterostructured nanoparticles, and then using our deep learning models with our representation trained on our data to then perform gradient-based optimization and discover new heterostructures that are very bright. So it all starts with data, right? We need to be able to generate a lot of this data. In order to do that, we need to be able to checkpoint our workflows because they take months to run sometimes. So we kind of instantiate all of our jobs. They're held in a central Mongo database. And then you just throw as many jobs at it as you can across as many computers as you can, self-checkpointing, saving the state of your trajectory in your Mongo database. One figure represents like so much work required to build this data set. And so we actually built kind of 4 different sub data sets. So I love myself a good acronym. This is only the first in this talk. The simulated upconverting nanoparticle spectra for emissions tuning, SUNSET. It's not bad. It's not bad. So the SUNSET data set has kind of 4 subcomponents, and we have kind of different dopants and whether or not there are surface ligands and fixed versus variable size. Just to be clear, though, I'm mostly going to be talking about or only talking about the results with the SUNSET 1 data set. Because this is variable size, this was vastly more expensive. We're dealing with particles of different size, different numbers of shells. This was actually about 5% of all NERSC CPU resources in a 12-month period to build this data set. And that's not because they gave me that amount because I asked so nicely, right? It's because we have these self-checkpointing workflows, which means we can run in low priority and just suck up excess cycles, just scavenge. Anytime there's an open node, we run for 45 minutes, then someone else comes in and grabs it. Well, we push things forward a little bit. So we just we're the bottom feeders here. This was more compute than the whole materials project in that length of time, right? Just scavenging at the bottom. So we built this data set very intentionally, where we have kind of an in distribution of kind of core only, core in 1 shell, 2 shell, and 3 shell, and then out of distribution with 4 shells. And just to kind of give you a sense of the distribution nanoparticle radius and log of the intensity, but we want to be able to actually do design on far more than 4 shells, right? So by having models trained on 0, 1, 2, and 3, and then you test them on 4, you can kind of quantify the ability of the models to extrapolate to a more complex heterostructured regime. So now we need a representation. And as I said, we don't, the exact positions of where the atoms are in these things is actually not important, nor do we know them, certainly experimentally. And so this is just like not really viable for these types of simulations, especially where we need gradients with respect to dopant concentrations and layer radii. You could use a tabular representation. And indeed, we started there. You should start simple before you get complex. If simple works, stick with simple. In this case, you can get the gradients that you want with respect to the dopant concentrations and layer radii, but the models don't work very well at all because they don't know that your ytterbium in layer 1 is the same as your ytterbium in layer 3. Those are just different columns. They don't know if those are the same thing. You could use an image representation. You could kind of voxelize up, these are kind of spherically homogeneous. So really you can just take a 1D vector of your concentrations at each distance away from the center of your particle. This works pretty well, as you'll see. We can get gradients with respect to dopant concentrations, but the layers now, they're gone. You voxelize them. You don't have any sense of like, basically there's no way to get a gradient with respect to the thickness of a layer, because that would just cause you the image to be voxelized, a little differently. There's no explicit layer radii that you can differentiate with respect to. So we needed something new. And of course, like from last slide to this slide is like a year and a half of work, trying things. And maybe again, not so secret sauce of machine learning is engineering, right? Chemical intuition doesn't get you much. You have to try things and try things and try things. And even then, a year in, we think, all right, now we've got a handle on it. And we try something. No, we didn't have a handle on it. We just got to keep trying things. We came up with a heterogeneous nanoparticle graph. Oh, one thing I just want to say, we've got these cute little symbols representing, the table for the tabular, the postcard for the image, and now this graph for our heterogeneous nanoparticle graph, where we have dopant nodes and interaction nodes. So we have two different types of nodes. They have two different types of features. And then you kind of, for each dopant in each layer, you have a node. So your ytterbium node in layer 1, ytterbium in layer 2. And then for every kind of pair of dopants that gives rise to interaction, you have an interaction node, and then you also have directionality. So you have the erbium to ytterbium interaction node going direction that way, and then the ytterbium to erbium directionally going back, because this is not symmetric energy transfer processes. And we've kind of got we embed the interaction type and the radii, the dopant types, et cetera. And then we also bring in the geometry of our system, right? We're dealing with spherical shells, and we can basically do this double integral capturing how kind of 2 points within 2 spherical or spherical shell regions can interact, where we have basically Gaussian distributions with learnable sigmas as in our integral that we're integrating over kind of all the pairwise points that can interact within these 2 regions. So I'm not going to say too long on this. If you do machine learning, you've seen diagrams like this before, but basically we have kind of like a machine learning potential. We're going to have an embedding of our dopant nodes on interaction nodes, and then we're going to do message passing with graph attention to kind of move information around and learn a better representation. So, just one thing I'll make a note of here is kind of the importance of these film layers, where you're basically taking information of different dimensionality and mixing them together. You could kind of just like take your elemental embedding and append your concentration of that element, but that doesn't work nearly as well as mixing them together with a film layer, which has a bunch of learnable parameters as well. So just some kind of machine learning magic machinery that actually makes a big difference. And then for our interaction nodes, we've got, of course, our dopant elements, as well as that integrated interaction term that all get mixed together. So you've got dopant node embeddings and interaction node embeddings, and then those all go into your convolutions of your graph attention message passing. So how well do we do? Well, our graph representation, kind of here, we've got our test mean squared error, and our graph representation in distribution performs, it's better than the image. It's not like massively better, but it's better. And both are substantially better than our baseline or our tabular approaches. But out of distribution, the graph performs massively better than the image. Note the difference in y-axis here, though, right? Like, it's not that out of distribution is easier than in distribution. It's that out of distribution, baseline tabular do very, very poorly, causing us to stretch our y-axis. So that was pretty cool. Again, we probably went through like 25 iterations of designing this representation, trying all sorts of different things to finally get to something that worked well. And of course, you got to show the diagonal plot if you're showing some machine learning results. Pretty good. Not perfect, but pretty good. Hopefully good enough to do some optimization and some discovery. So another thing, though, that kind of came when you're thinking about representations is about invariances. So like for a molecule, if you rotate your molecule, right, you're going to have the same energy. It's the same molecule. Like we don't think of molecules as, a molecule certainly doesn't change when you rotate it. And the equivalent for a nanoparticle is you could just arbitrarily like think of two regions as being subdivided. So here you just have a full homogeneous core, and now just call it a smaller core with a shell, but the same concentrations, right? Like those are the actual nanoparticle you have, it's totally identical. But the graph that you have is not identical, which is awkward because you're basically making the problem harder. If you know physically these is exactly the same thing, but they have different representations, then the problem is getting harder than you want it to be. We spent a lot of time thinking about this. You can make them mathematically equivalent if you get rid of all of your nonlinear operations in your machine learning infrastructure, which if you know anything about machine learning, that is very bad. Basically, like all the power of machine learning comes from the nonlinearities. So that's a bummer. So instead, we can just kind of do the other obvious thing, which is we can do data augmentation. Just like with images, you can rotate an image of a puppy, it's still a puppy. You want your CNN or vision transformer to know that. So here, what we can do is we can at train time, we basically, within a mini batch, we are randomly subdividing each nanoparticle up to 3 times with a minimum region radius of 0.1 nanometers. So that means that kind of every epoch through, you have the original unsubdivided nanoparticle in your mini batch, and then you have that same nanoparticle again with like some number of randomly inserted subdivisions. So every epoch, it's seeing the same fundamental data, but different graph representations of the exact same data. And that actually kind of quite dramatically drove down model error. We also tried to put a term in the loss function that, to drive down the difference in the latent representation of the subdivided and unsubdivided nanoparticles. That didn't work so well. We're not totally sure why. Basically just drove all the weights to 0 rather than, so anyway, this worked well enough. We were quite patient on this project, going all the way from data generation to representations to models to optimization. So at some point, you gotta move it along, and we felt like this was good enough. So now we've got our model, and we can get the gradients that we want to do optimization. You give the inputs, the layer radii, the concentrations. You kind of do your forward pass to get your predicted emission intensity, and then you can back propagate to get the gradient of that emission intensity with respect to each of these heterostructured parameters. And then we can run optimization. And now we don't need to do Bayesian optimization. We can do first order optimization. And really what we do is a global optimization of basin hopping, where within each basin, we're doing kind of first order optimization. And then you can make nice, pretty movies. Who doesn't like that? So here you're just like watching the nanoparticle optimize, and it just kind of keeps changing, and the UV intensity keeps getting driven up. And you end up with this kind of like zebra structure of different dopants kind of separated in different regions. And this was kind of in line with what might be expected, because people have kind of manually optimized like the 3-layer dopant. But even still, I mean, Emery sees these and he's kind of blown away, because he could never have imagined like intuitively coming up with exactly this type of structure. So now the question is like, all right, we trained a model and we ran optimization. Did we actually predict something correct? And what some of you might want me to show is, yes, we made the particles and they're perfect, right? But come on, we can't do literally everything in one project. And making a 10-shell particle is not a walk in the park, as I think at least one person in the audience would be certainly right. So the question here is not, did we match experiment, but did we match the underlying KMC, right? Because we're making a surrogate model to predict the output of our KMC simulations, which are currently our ground truth. Whether there's a gap between the KMC and experiment, you could always just kind of fine tune the model later on some experimental data if this is working to kind of get a good representation and predict your KMC outputs. So I love this plot. Basically, this is each one of these boxes is a global optimization. Okay, so we have on the x-axis the maximum nanoparticle radius, and the y-axis the number of regions, the core plus the number of shells. So for each of these, we're doing this, basin hopping plus gradient-based optimization to find the optimal nanoparticle heterostructure to maximize UV emission pursuant to this specific number of this specific maximum radius and number of shells. And in the lower half of the box, you've got the ML predictor, what came out of our model. And in the upper half, you've got what we get when we run the KMC. And I just want to be clear that running this whole grid of optimizations took like 2 days on some GPUs with our trained model. To run all of the KMCs to validate all of these boxes was 3 months. So now imagine trying to do the optimizations with if getting just the final optimized particle simulated with KMC takes 3 months. I mean, yeah, it's just totally impossible to do optimizations like this using the KMC, even if KMC gave you gradients, which it doesn't, right? So it's both much faster and gives you gradients, allowing you to do these optimizations. And what blows me away is that kind of this in orange can be thought of, the orange outline region can be thought of as our like in distribution as far as the radius of the particles we trained on, the number of regions that we trained on. Everything else is out of distribution in multiple ways. And the maximum intensity, the brightest particle in our training set is right around here. We are correctly, successfully predicting things that are out of distribution along multiple axes, which validate against 3-month-long KMC as being super bright, way brighter than anything we've trained on. Pretty sweet. And to just kind of show you what some of these heterostructures look like, this is the I particle. So even kind of in distribution, we got something that had 2 times higher intensity, UV intensity than anything we trained on. And then out of distribution, we got something 6.5 times higher UV intensity than anything we trained on. So really, this was funded by kind of LBL internal money, and that meant that we could be patient. We didn't have someone breathing down our neck of like, get out incremental papers. And that allowed us to go all the way from building the workflows and implementing the C++, to building the data set, to coming up with the representations, to training the models, to doing the optimization, and kind of discovering these wacky, interesting new heterostructured nanoparticles, which Emory is now trying to make in the lab, of course. So that's kind of the end of this section. I'll just give credit to a lot of the people who did so much of this great work. Eric Sensei and Lucas Atia, especially Evan, Ben, Daniel, Xiaojing, and Emory, who, came to me with this, oh, can we do machine learning on these nanoparticles? And taught me everything about nanomaterials that I have certainly learned since I was in undergrad, long time. So, and then LBL for funding and NERSC for letting us like scavenge at the bottom of the pool of their compute. All right, so now we're going to change gears dramatically to something that's much kind of closer to what I usually do and think about and have cared about for a long time: chemistry, reaction networks, and machine learned potentials. So I love to think about complex reacting chemistry. Started in my postdoc thinking about batteries and SEI formation with Christine. Now thinking about nuclear nonproliferation and semiconductor manufacturing, photolithography and polymers. I've got someone who wants us to do this for wildfire chemistry to understand the species that get deposited in the soil after these like really hot wildfires. All this complex reactive chemistry is all around us. It's kind of central to everything in our daily lives and technology that we care about. And it's really difficult to pick apart. You can't intuitively make your way through a map of thousands or even millions of possible reactions, and you can't intuitively come up with what the most important reactions should be. But if you have a reaction network, you can identify the important species, you can come up with identify the important reaction pathways, simulate the time dynamics of your system, and actually understand and then hopefully control such a complex kind of reaction cascade. But to do this, there's this one little pesky thing that you really need, which is transition states. God, transition states. They've been a pain in my ass and a lot of other people's asses for a long time. A good friend of mine spent 1.5 years in his PhD looking for one transition state. He didn't spend every hour of every day of that 1.5 years doing it, but kept coming back to it, trying new things. I mean, one transition state. I just said we need thousands, maybe tens of thousands, and they're really everywhere. Optimizing to potential energy surface minima, not so bad. We're pretty good at that. Optimizing potential energy surface saddle points, much, much more difficult. And they're everywhere: soot formation, electrolyte decomposition, polymer recycling, catalysis. Every one of these things I circled in red is a transition state optimization that someone had to do painstakingly. painfully, perhaps. And if I want to build these big reaction networks, then I would need to be able to do this in high throughput robustly. And we've been trying to think about ways to do this for a long time. Kind of common double-ended methods, because I think about it in the context of reaction network, I can map out like all the species that I might be interested in. Even that's kind of a separate problem. I think of them as separating them into two problems. So now I'm going to know my reactants and products. I need to, this is the double-ended context. If you know the two minimum you're trying to connect, to look for the saddle point connecting them. People use nudged elastic band, where you have this kind of discretized bead and spring approach. They also use the growing string method, where you kind of grow your beads and strings dynamically. From Graham Henkelman kind of came up with NEB on the left, and Paul Zimmerman really popularized the growing string method on the right. But there's the discretized path is fundamentally bad. It doesn't optimize cohesively. You're kind of moving each bead by itself. The path can break. It can fail to connect in GSM. You completely miss features of the potential energy surface between the beads. There's all these hyperparameters. If you're like a real good expert with one of these methods, you can kind of try stuff and usually, not always, but usually get it to work. But I can't do that if I have thousands of transition states I need to find. Also, one thing that we've kind of realized throughout this project I'm telling you about now, finding the minimum energy path is the wrong goal, in my opinion. If you find the transition state, you can always run an IRC and get the minimum energy path. Why make the path optimization harder when you just need to find the transition state? And just to show you that people keep publishing methods trying to make transition state optimization better, I'm just going to assert by fiat that if this was solved, people wouldn't continue to try and solve it. So it's definitely not solved. But there's a key kind of unifying factor here. All of these methods were developed within the constraints of using a DFT PES. And I think we're really on the cusp of a revolution with these machine learning potentials, where now the machine learning potential is a surrogate model for DFT. You give it your configuration, you get your energy and forces. You may not get all the interesting electronic properties that you might want, but you could always take something optimized with MLIP and then just run a DFT snapshot and get those properties. Or maybe we'll have other ML models that will learn the electronic properties as well. And as we see here, this is from the kind of the OC20 leaderboard. They put together this big data set, they build a leaderboard, and if you build it, they will come. People have come up with better and better architectures over time, driven down the errors in these models. And here's the materials project, Matt Bench Discovery Leaderboard, a similar idea, but for solid state materials rather than catalysis. And just in the last year, I mean, basically every model above base MP0 is from the last year. So people are really rapidly pushing forward the accuracy, the boundaries of what can be accomplished with machine learning potentials. And I've got something really exciting coming in 2 weeks that I cannot talk to you about, unfortunately, but keep an eye out. We're really on the cusp of a revolution as far as machine learning potentials being within the realm of kind of replacing DFT for broad swaths of atomistic simulation. And so already people are doing transition state optimization atop MLIPs. This was from the group at Meta, doing NEB atop their OC20 potentials. And this great paper came out recently of doing the growing string method atop a bunch of these molecular trained MLIPs. Alexander Isaev just had a paper come out in arXiv like a month ago where they're doing kind of a combination of different transition state optimization methods for these palladium catalyst systems atop MLIPs. So people are already doing this, right? But what I want to point out is that for more complex reactions here, you're getting lower NEB convergence. The growing string method and Chenru and Chiwan's paper is getting less than 70% of the intended reactions. There's lots of room for improvement. And the obvious place to go to start to improve is differentiability, because the MLIP is automatically differentiable. So we kind of had this idea, I was kind of asking people about this at a workshop in 2021. Like, why don't you just auto diff again and get the Hessian at every step of your transition state optimization? Because that second derivative information is crucial for transition states optimization, for optimizing to those saddle points. Way more important than it is for minima. It's still important, but it's not nearly as important. So, all right, you auto diff from energy to get your forces, auto diff from forces to get your Hessian. I mean, sure, you pay a little bit more cost, but it's an MLIP. We use that, you have to do with DFT. right? This is fine. This is not that big of a cost in comparison. And this work published in Nature Communications, we show that if you use the full Hessian at every step of the TS optimization, it takes half as many steps to reach convergence. You kind of take larger and more confident steps and more direct paths. That's kind of what this is showing, that the mean step size is larger. The optimization path length is shorter. You're just taking a more direct route to the transition state. Far fewer steps on average, higher rate of convergence, more likely to find the intended transition state, and you're more robust to degraded initial guess structures. So there you go. AutoDiff, use that second order information, improve your transition state optimization. But this is single-ended, right? Here you kind of already have a transition state structure guess. But what about the double-ended context, right? What about actually doing a path optimization between two minima? Can we also leverage this differentiability to improve robustness? So kind of our goal, right, is a robust double-ended transition state optimization, leveraging continuous path representation and MLIP differentiability. What don't we want to do? We don't want to discretize the path. Beads and springs, don't want to deal with it. They cause so many issues. And we don't want to worry about recovering the full minimum energy path, just the transition state. What we do want to do is get the top of the path as close as possible to the TS by leveraging a suitable path loss function, cohesively optimize the entire path, adaptively sample bumpier regions of the PES, and leverage that second order information for improved robustness. So the first question is, how should we represent the continuous path, right? If we're getting rid of these beads and springs. People in the past have used kind of basis functions, Schlegel from 2015. This introduces a whole bunch of other issues. Come on, we know it's 2025. We know what to do. Let machine learning take the wheel, right? Just use a neural network to represent the path. The input is like your time, t equals 0 is your reactant, t equals 1 is your product, theta are your learnable parameters. Your output is the 3D structure at time t. Just kind of use, and this way, by using a neural network, we can kind of leverage modern deep learning training machinery to optimize the path. Training a neural network is just doing an optimization pursuant to some loss function, tweaking your learnable parameters iteratively, driving down your loss function. So here, if we have a path loss function and the path represented by the neural network, then we can just train the neural network to do our path optimization. And we avoid systematic error from these kind of basis descriptions. We enforce fixed endpoints with a hard constraint. This is not a massive neural network, right? For like a 10 atom path, you're dealing with like 1,000 learnable parameters. Not crazy. The other thing here is that when you have a neural network, right, changing an internal parameter, this is a fully connected neural network. It changes all positions being output. This is kind of like internal coordinates that are so essential to molecular geometry optimization. So we've got a representation. What is the best path loss function? And I hope that you will bear with me as we actually do the faux pas as a chemist of putting some equations on the screen. Bernhard Schlegel, kind of known as the godfather of molecular optimization. Most of the kind of the best optimizers that we use in our quantum chemistry codes are based on Schlegel's work. Schlegel had this paper a decade ago, which I think only has like 10 citations. No one ever really seemed to find a use for it, where he came up with this idea of the variational reaction energy, which is an integral over your path, over your reaction path, of the force, the magnitude of the force times the magnitude of the velocity, right? So the magnitude of the force is just the PES force at your point along the path, and the velocity is the basically tangent to the path at that point along the path. And the VRE is minimized by the minimum energy path. So Bernie tried to do all this optimization of the paths using EVRE as the quantity to drive down. But he also defined this other thing, this PVRE, the projected variational reaction energy, which is the projection of the force onto the velocity, which is minimized by the path which goes least high. In other words, it directly targets the transition state. You don't worry about the whole path being the minimum energy path, just the path which goes least high. He basically used this to find some variational bound and then never used it again, just kind of threw it to the side, didn't care about it. But the more we chewed on it, we thought that's actually what we want to be doing. We want to be finding the path which goes least high, which should thus go through the best transition state. And so we think PVRE will work better than VRE. But we're not going to assume, we'll test, I'll show you. Another thing though, to note about PVRE, it allows you to traverse ISO energy lines for free. Because if you're moving on an ISO energy line, then your tangent to your path is zero. I mean, the projection of your force onto your velocity is zero. And that kind of feels, I mean, in the quantum world, ISO energy is basically equivalent to ISO probability. And indeed, like you do want to allow your optimization to kind of, easily traverse and explore things that are ISO probabilistic. So we kind of think that PVRE is not only doing what we want as far as targeting the transition state, but that it should actually make the optimization problem easier for searching through a high dimensional search space. So regardless of which one we're going to use, we have to calculate the path loss via a numerical path integral. And we're going to use an auto differential ODE integrator. And typically you do a sequential one where you kind of grab one point and evaluate it, and then you use your bounds to figure out the next point one at a time. But we really want to be able to speed these things up via parallelization on a GPU, right? We want to be sending a whole bunch of snapshots all at once, asking your MLIP for one energy and force versus for 1,000 energy and forces is the equivalent time cost, as long as you can fit in the memory of your GPU. So we basically came up with this a parallelized adaptive integral using batched MLIP evaluations, and in the end we get almost 100x speed up for a GPU parallelization. So even though it's an MLIP, you still need to be clever about your engineering in order to make this fast and kind of tractable. But in either case, you're using an adaptive sampler, you're going to sample bumpier regions of the PES more densely. So don't need to worry about a perfect time grid and cross your fingers and hope nothing weird happens in the PES between your 2 points. You're going to capture the full PES along your path and capture bumpier regions more. So now we're ready to optimize, right? We've got 2 possible loss functions. We've got a way to calculate it fast. And so now we need to auto diff the loss to figure out how to change the learnable parameters in your path neural network to change the path, to optimize the path, which means since your loss has terms that are the gradient of x, the gradient of your loss will have terms that are the second gradient, second order gradient of x, which is inherently the Hessian. So you have to have a differentiable surface to do this. You could not use this method atop DFT. I mean, you could, but you'd be waiting years for it to converge, basically. And so yeah, we're differentiating with respect to the neural network weights, which parameterize the path to pursuant to that loss function, drive it down. So you calculate EPVRE with the path integral, you auto diff, you update the weights of your path neural network with stochastic gradient descent. This is basically training a neural network, right? Your forward pass, your back propagation. But just to be clear, yes, training an MLIP is very expensive. Training this simple little path neural network, super cheap. It's like the same cost as NEB. No need to stress about the fact that I'm calling something training. Okay, it's just an optimization. So again, I'm a fan of good names, of good acronyms. I gotta blame my old boss, Alanis Berguzik, for that. These days he's looking pretty cool. Back then, a little bit dorkier, but he instilled in me the importance of a good name. And so we call this path optimization with a continuous representation neural network, or popcorn with 2 N's. You got to have something that makes it easier to Google, right? If this was a single N, no one would be able to Google this method. So it should be a word that you can remember, but spelled slightly wrong so that people can Google it. It's always a fun challenge. Thanks for that lifelong lesson from Alon. So now on a model potential, right? We're going to do VRE versus PVRE just to see, kind of which one works better. So we're going to watch VRE, and it's trying to find the minimum energy path. So it got to the transition state around the 300th iteration, but you could see it was kind of struggling, right? It was struggling to climb the hill. PVRE, 70. You're there, right? It just slides right up the transition state. You're not worried about the whole minimum energy path. And in practice, what we've seen, kind of consistently across all examples, atomistic and toy models, is that PVRE finds the transition state much more robustly and much faster than VRE. So minimum energy paths are the old. Let's just find a transition state, focus on what we care about. You can do an IRC later. It's not that big of a deal. So, all right, we've got everything we need to actually start doing some chemistry, except an MLIP. right? You need an MLIP which actually is accurate for the transition state region or for kind of the types of reactions that you might care about. A few years ago, Grambo Green released this data set of reactant transition state product trios, almost 12,000 at a pretty good level of theory. And then a couple years after that, Schreiner et al. Basically ran a bunch of lower level theory NEBs on these reactions to generate a data set of snapshots of structure, energy, and force to train MLIPs for, that could work for transition states. Not a fan of their level of theory, but, give me 2 weeks and that'll all be solved. I'm not kidding. In 2 weeks, you'll never need to use this data set ever again. But for now, we're dealing with MLIPs trained on this data set. A couple of notes here. I'm going to be talking about 2 different reaction kind of validation sets of 960 or 1021 reactions. I'll describe them. Also, there were 1,888 reactions which failed the DFT NEB that they did. So that is kind of going to be our challenging test set of reactions, which are the 960 and 1021. They're not in the training data, but NEB converged for that. The 1888 NEB didn't converge. Get to a nice little stratification here. So what are we trying to do, right? In order to evaluate the efficacy of double-ended transition state optimization, you have your 2 initial endpoint structures, you optimize them on your PES, you then perform the path optimization from those 2 minima, growing string method, NEB, popcorn, take your pick. You then we take the structure at the top of the path and do an actual transition state optimization on it. Just because your NEB converged or whatever doesn't mean that you actually found a transition state. You then need to do the TS opt. We're going to use our favorite optimizer, Sella, which is the best transition state optimizer in the world. And we use the full Hessian at every step from MLIP autodiff to do the TS opt. And then you run an IRC from the converged transition state to endpoints. And then you check, did I find the endpoints that I wanted, right? Like by comparing the bonding. And so kind of what you can get is you can get a 2-end match. You got exactly the endpoints that you wanted. A partially intended, you got one of the endpoints you wanted and one not so much. No match, where neither endpoint looks like what you wanted. Or you get no reaction, right? Where the endpoints are the same kind of bonding graph. And of course, you can also fail. So these are kind of the 5 possible outcomes, and I'm going to show you a bunch of kind of bar charts of outcomes on these different evaluation sets. So here this is collaboration with Teresa Gordon's group. So we're using her favorite equivariant MLIP Newton net trained on transition 1x. And first we're going to compare it to NEB. So these are, we need to converge NEB with respect to number of beads because we're going to run lots of samples of the path. So we don't want to just basically be getting a better result with our path opt because we're sampling the path more. We ran NEB with 10, 100, and 1,000 beads. And actually 100 was better than 1,000. So, more beads is not always better for NEB. We're dealing with these 1,021 reactions where we have validated that a transition state exists on the Newton net PES for this reaction. So if we fail to find it, it's a failure of the method, not the MLIP, okay? And here, so there's different ways you can initialize your NEB. You can just do linear, there's IDPP, this geodesic work from Todd Martinez's group, and people kind of over the years have gotten better at initializing your NEB path optimization. 86% on these 1021. I mean, it's not bad. I want better, but it's not bad. If we use our method, we're at 95%. And almost, I think we only have 1 failure there at the top. The other thing though is that you can use our method, there's a reason I have this labeled popcorn, right? I'm not just trying to be confusing. We're using our continuous machinery to initialize the path with the geodesic loss function and model potential. And then we take that initialized path and we put it on the MLIP and do the path optimization. So we're using popcorn for the path initialization and popcorn for the full path optimization. You can also use popcorn for the initialization and then feed that into NEB for that path optimization atop the MLIP. And I have to show this, you'll see why on the next slide. But in this case, using popcorn for the initialization with Todd Martinez's kind of geodesic loss and kind of fictitious potential, it helps, but not a ton, right? We're getting the big jump from using popcorn on the MLIP. And just to call out, I mean, look at all these failures that you had, right? We're basically replacing failures, the worst possible outcome, with two ended matches, the best possible outcome. So it may not look like the biggest jump, but ask anyone, I mean, 87 to 95, if you're dealing with 1,000 reactions, that's going to make your life a heck of a lot easier. And almost no instances of no reaction either, which is also just kind of a ubiquitous failure mode when you're dealing with double-ended transition state optimization. So now we go to our harder set of reactions, right? And I said we had 1,888, and of those, 1,353 successfully validate on the Newton net potential, MLIP PES. But you can see they're much harder, right? Already, I mean, the linear interpolations get you almost nothing with NEB. And even with the geodesic, you're only at 70%. And with popcorn, we're up to 90%. Here, interestingly, we get a lot of that jump just comes from initialize, we can recover a lot of that jump from the way we initialize NEB by using our method to run the path initialization part of the procedure. So it's not entirely clear to me why we get, why we see this kind of orange versus red behavior. But either way, I mean, the fact of the matter is this is kind of current state of the art, and this is with our method, 20% improvement in robustness. Pretty exciting if you think about high throughput transition state optimization to build reaction networks. And again, in this case, I think there's, again, one failure total. We have basically taken all these failed cases and converted them into double-end matches on average. So what about growing string method? There's this great paper that came out from Jiwan and Chenru, and I swear I'm almost done, where they kind of trained all these different MLIP architectures on transition 1x, and then they ran GSM on some reactions. And I think 960 reactions. And they basically saw that the MAE, the energy and force MAE of their models directly correlated with the success, almost, except for orb, but I don't want to talk about that. Besides direct force models, directly correlated with the success of their TS op methods. But 660 out of 960 is not great. So we went ahead and they also ran their GSM with 9 beads. I presented some of these results at ACS. Paul Zimmerman was in the front row who invented GSM, and he suggested we up the number of beads on GSM to 25. Just like with NEB, we don't want this to be a matter of we didn't give it enough beads, right? So, and here though, a key distinction, these are reactions that are validated as having a TS on the DFT PES, not on the MLIP PES. So some of these failures are due to MLIP error with respect to the DFT, and presumably as you get to higher errors like on ANI1X, more and more are going to be issues with the underlying MLIP PES. So we did our own GSM with 25 beads. We bump up the success rate a bit. We use Sela instead of their optimizer also. But still, I mean, for the, and again, we see as they saw the kind of correlation between model error or anti-correlation. Lower model error is higher GSM success. And then we go to popcorn, and again, all the numbers get a lot better. And we still see the same correlation, but and these on all these 0 failures across the board, which it's just a personal point of pride. So kind of wrapping up here, we kind of came up with a double-ended transition state optimization method we call popcorn. It cohesively optimizes the entire continuous path by training a neural network. It adaptively samples bumpier regions of the MLPES along the path in parallel, leverages the path loss function that targets and gets most closer to the transition state itself. Depends on autodiff and leverages second order info. We're still tightening a couple screws, and we want to make sure this works for periodic boundary conditions so we can do catalytic reactions, hoping to put out a preprint and code release in approximately 2 months. And with that, I just want to kind of give you a vision for the future that I see rapidly approaching, which is that in the not too distant future, we'll have these foundational MLIPs trained on molecular, solid, and interfacial DFT that can handle variable charge and spin, cover most of the periodic table, can deal with condensed phase reactivity, can be fine-tuned when necessary to specific systems of interest with modest amount of initial data. At that point, transition state optimization and path optimization methods built for MLIPs will allow us to build massive reaction networks of complex systems and pick apart complex reactivity rapidly and robustly. And with that, big shout out to Kareem and Eric, who've led the popcorn work, the Center for High Precision Patterning Science, and LBL for funding, and all of you for your attention. And I just want to leave you with, I got to put up some movies, right? Popcorn versus NEB, right? I'll just hit play on both of them, and you can watch NEB do some wacky stuff. Popcorn, just nice and smooth, no problem. And if you look at the force plot, right, your transition state force should be 0. So you look at NEB and you're like, well, is that the transition state? Is that like where is it? Right? Popcorn, very clear. It's right there. No problem. So anyway, thanks so much for your attention. Happy to take questions.
Great, cool stuff. Thank you. Questions? Someone.
In popcorn, do you train your network for every different reaction pathway?
Yeah, I mean, you're doing a path optimization, like you're doing a path optimization for each new reaction, right? Like it's not an MLIP, you kind of train it once and then you just apply it over and over again, but each reaction is different. It has a different transition state. I mean, I think there are interesting questions about are there ways to pre-train like this path neural network to make it better, to make it easier to optimize to any transition state? Like there are some interesting questions there, but in general, you're going to initialize the path freshly for every reaction and do your optimization for every reaction, but it takes like 2 minutes. So it's not like we think about training an MLIP as being like hours and weeks or whatever. 2 minutes, it's fine. Yeah.
You said that the popcorn is more smoother and everything. That I agree. What's the actual success metric? So do we know what correct is?
I mean,
I don't think that's NAB necessarily, but like, so what do you measure against when you say NAB failed and this one succeeded? So like, what's the measure?
well, that's did you recover the transition state that connects the two endpoints that you started with, right? Because you're trying to find a saddle which connects reactants to products. And then you give the reactants to products as inputs. And then you run the path optimization and run the TS op and run the IRC and you see, did I find a transition state which connects?
But that is not guaranteed that this is the correct one. Look, I'm comparing this sort of to quantum chemistry situation in DFT, where we can gauge a functional against quantum chemistry, and we know is it a good or bad functional.
Yeah.
Do we have something like this here or no?
No, I mean, it
Could
depends.
a transition state, I mean, I can guess some, and this will be a transition state, but if it's a right one, that's the question.
I mean, here we're assuming that our MLIP is correct, right? It's just a matter of navigating the surface. Just like, I mean, if I'm going to do molecular DFT, I'll run Omega B97MV, DEF2TZVPD, and I'll like, if I find a transition state on that surface, then I'll assume the delta G for that barrier is good enough. In the molecular world also, our functionals are just like way better than in the solid state world. So like people have rigorously benchmarked these functionals against coupled clusters, CCSD per NT. So you can kind of trust your level of theory more. And now here, yeah, so you can trust it, but here it's a matter of, do you have an MLIP which accurately reproduces your level of theory, which you believe accurately reproduces coupled cluster, like exact electronic structure. So, I mean, you're kind of a couple layers away from, yeah.
Electronic structure method, and this is about the relaxation, the ions.
Right, so the MLIP is trained on DFT, and the DFT functional was fit to coupled cluster, right? So the DFT functional should give energies and forces and delta E's and delta G's or whatever that are, if you go look at Martin Head Gordon's papers, you'll have all the metrics of how close they were able to get Omega B97 MV to match coupled cluster, right? And then with that, you have a degree of kind of confidence in the results of the DFT, and then you have your error measures of your MLIP to your DFT, so you know how closely your MLIP is going to reproduce DFT.
Yes.
Right? So this is the whole idea of this method is under the assumption that we have an MLIP that we think is well trained against high quality DFT. And my kind of what I'm positing is that we will have such an MLIP, a general purpose MLIP or a fine tunable MLIP for a broad swath of chemistry in the near future. Given that, then the ability to find the saddle points on the surface becomes the bottleneck.
Mm-hmm.
So we're standing on the shoulders of giants here, very much so.
Speaking of shoulders of giants, Aaron. You're the growing swing guy, aren't you?
I'm not Paul Zimmerman. I am sitting in the back row. I invented a growing string method. Anyway, it's no problem. I actually don't like that paper, my own paper. And I think that I'm really glad to see like improvements being made on it that are like really good. But I think that the example that you conclude with right here is one of the main modes that I see these calculations fail when we use them. And it's that you have to anticipate which atom goes. So you have a three-dimensional geometry here.
You're talking about the atom mapping problem? Yeah.
You have an atom by atom mapping. And in the popcorn one, you've chosen it to make that mapping very simple. And it becomes a linear path. in the NEB path, you can see that the atom by atom mapping was done wrong. And the molecule has to rotate first to transfer the hydrogen that's in the active state.
The mappings here should be identical.
I mean,
We work very hard to
yeah.
ensure that we're giving NEB and popcorn the exact same inputs. We do have to deal with the atom mapping problem, but it's done beforehand. So then,
Rotation before the transition goes, which suggests to me that the hydrogen mapping was flipped.
I think probably what happened is it found a transition state, which then, or no, I guess this is the NEB path, not the IRC path. I'll have to check, but I'm intimately aware of the atom mapping problem, having been screwed by it many times. So, I mean, we attempted to be very rigorous here in our NEB versus popcorn comparison.
I can sneak in another question.
Yeah.
There was a comment in here about this PVRE criteria. Really
Yeah.
clever. I really love. There was a comment in there about it allowing you to trace some iso energy lines, but in a high dimensional space, these are like enormous high dimensional manifolds themselves. What role do they play?
You don't trace them. It allows your path to spool out along an iso energy line. Your loss function does not increase when your path is traversing an iso energy line. So you're not like, when you think of the minimum energy path, you should always kind of be going up or down. Like you never just want to be like hanging out, moving along an iso energy line. But because it's the projection of the force onto the velocity, your velocity on an iso energy line the projection of your force onto they're perpendicular if your path is moving on an iso energy line, because, right, like the force is going uphill, the iso energy line is just going across the hill.
Having a component of your path.
Right. So you allow the path to do whatever it wants as long as it's staying in that segment of the path, it's staying on an iso energy line.
Is that piece help you somehow?
We think so.
The criteria passes through the top points.
It's a good question. I'm not positive. But what you see here, right? I mean, it's up there, right? It just goes right up and then it just hangs out at high energy. I mean, you're kind of seeing the effect in this example in the upper left in orange of popcorn just goes right up and then it just looks around on basically iso energy lines, and that allowed it to find the transition state kind of faster, and one that is, or the path makes a bit more sense. So, I mean, I think that we've kind of had some intuition here for like what could make things better, and then we try it and then we see what it does, but like whether or not it's better because of our intuitive kind of prescription for why we thought it would be better or not is like a really, really reasonable and good question. And I'm sorry if I didn't give proper credit. I did intentionally say popularized.
Simon says my worst paper with the whole citation. The paper is just incrementally different from NEB. I agree that there's a lot of room.
But thanks for the great questions.
All right, well, in the interest of staying approximately on time, let's thank Sam for a great talk.